set of nodes, right? So socks always goes out to some other particular part of the graph. Undershorts always go out to some other part of the particular graph. Then we have something in between where some of the nodes end up into pants, and pants also goes to some other sort of nodes, right? Then we have the very other end of it where the node does not have any outward edges, but only has inward edges. We call those nodes as sink nodes. So source nodes are where you always have things coming out, edges coming out of your node. Sink nodes are where you always have edges coming inside into your particular node, right? So a DAG can be linearized by decreasing the post number in order of the decreasing post number, because the smallest post number has to be a sink, right? And the highest post number in that scenario has to be the source. Remember that example we had, A was basically the source because all of those other edges or all of those other vertices are child nodes of that particular root A node. Okay. So that was directed graphs and how we can figure out if a particular graph is a cyclic graph or not. The next thing that we will look into is called strongly connected components. So before we begin, any questions about directed graphs so far, or directed acyclic graphs so far?
I think I'm a little fuzzy on the algorithm that actually determines.
Okay. So, given a graph, right? You have this particular graph and you have represented it as a adjacency matrix or an adjacency list, whatever, does not matter. You perform DFS on it. Now, DFS gives you two values, right? The pre-values and the post values. Now, the post values essentially can be used to linearize the order of your graph. Now,
right.
Given these post values, I am basically, so socks is the node that has the highest post value. So you can imagine in your recursion tree, the last function call will be for socks, and then after socks, nothing else is called, and it pops back out, right? So
Yep.
that gets you the largest post value. Now, in that scenario, once you have that particular post value, you would then keep on adding it to the linked list in that order. You would always, once you come out of that and during your post visit operations, you would be inserting that particular node in that particular reverse order into the front of the linked list. So if you do so, then all of those nodes should have a descending post order until and unless there is a parent node that there is a child node that connects back to the parent. In that sense, in that case, the position of those numbers or that order of those would be hurt. Otherwise, you can always, if there is no cycle, you can always insert it to the linked list in that particular order where all the edges go from the parent to the child. Does that make sense?
I guess I'm a little hung up on so like going back to that example where you had like the 4 nodes with A, B, and C.
Okay.
Right, that one right there. So when I'm down at C, I would go look at A, but then I wouldn't actually explore it because I would go look at my
exactly, because that would end up getting a cycle, right?
Right. So then I would never assign a post a post value to.
No. We are not using a topological sort. I'm not saying that topological sort or DFS would fail if it's a cyclic graph, right? It is still going to get you a list of nodes and some set of post values as a tree, right? But in order to check for a cyclicity of a graph, you have to check for back edges. And the only way of checking back edges is you would need to check whether a particular node, in this case A, has been pre-visited or not. If it is not visited at all, then it's fine. If it is completely visited, as we had that particular example where this particular set of nodes were completely visited. right? So if when we talked about here that these particular, so with these particular set of nodes were completely discovered before we moved on here, because we can't move to that particular location. In that case, we have already post visited this particular node. That is fine as well. The issue comes when you reach a particular node which has a back edge back into a particular parent, right?
Right.
Yes, and a topological sort essentially helps you figure that out, because in that scenario, you would then have a back edge. See, once you're done with, while you're building that topological sort list, right, you are always going to check for other edges as well. So let's say that I'm in shirt, right? Take an example, I'm in shirt and I'm going to check for all nodes connected to shirt, right? And for that matter, let's say that shirt is, yes, let's say that there is an edge that connects to pants, right? Let's just assume that this is a crudely drawn arrow, but you guys get this, right? From shirt, there is a connection to pants, right? Could you type in yes or no? I could make my drawing better. Yes, yes, okay. Okay, so now in that scenario, once I'm inserting shirt, I'm also looking at the other edges, right? Now imagine if you're given an entire V squared matrix, and then you would have to figure out all of the parent nodes and all of the other possible paths that I can find. But a topological sort now tells you that you only need to look at these set of nodes that have come before shirt. You don't need to care about all the other nodes that we have not done yet. Does that make sense? So when I say that shirt has a connection to pants, you say that there is a back edge to pants and pants has already been discovered. So in that scenario, this is not a cyclic graph, right? You're
Right.
still,
So,
yeah.
but the way that's working is your DAG, or no, not your DAG. The DFS is going to return an array of pre and post values, correct?
Yes.
And that's what you're using to go check for back
Yes,
edge.
so, yes, so my DFS is going to return me a pre and post set of values. And once we are done, we are basically pushing all those vertices into a linked list in that order of post values, right? So once we are inserting them in post values, whenever we insert into the front, we are checking whether we have any back edge into a previous set of nodes. Now this basically reduces the complexity to V, because essentially inserting an edge and checking if an edge is already visited or already inserted into the list is V, right? And then essentially we are checking if we have that particular node that has already been inserted in that list. Does that sort of make sense? As to why the complexity is still V plus E.
Yes, I think so.
Okay. We can talk about it in more detail later. Just go through it and we can again discuss this in the next class. Okay. Yes, socks over under. So we talked about source and sink graphs, and now let's talk about strongly connected components. Now we talked about directed cyclic graphs and we talked about directed acyclic graphs. Now strongly connected components are essentially a way of breaking down your graph into smaller components where each component has a cycle, or basically from each component, from any node in that component, you can reach any other node, including itself, right? So if I look at this particular graph example here, we have an edge from A to B, B to C, and so on. You guys can see this particular graph. And now note this particular strongly connected component outlined in dots. So one can reach F from C, and one can again reach C from F. So this entire two set of nodes becomes a strongly connected component, right? For example, take the more bigger graph here. So from G, I can reach H, K, L, J, I, and G. So that is a path. And so from G and J, I can connect G to J here and then come back to G as well. So that is a cycle as well. So all of these nodes, if I start from any node, I can reach any other node, right, in this particular component here. Similarly for B and E, we can reach both of those nodes if I start from any other node. See, this is not an issue in case of undirected graphs, but in case of directed graphs, we are not only checking for cycles, but we are also checking if we can access all of these subcomponents within this particular graph. And then we are just saying that if that is the case, then this is a component and I just need to, okay, so the reasoning behind, think of strongly connected components as this. So let's say that you want to reach the node L starting from the node A. Now you can either start your entire search process by checking for B, then E and G and then J and so on. But you can reduce your search process by just saying, I just need to reach either node B or E, because both of them are connected. I don't care which one I reach. And then I need to reach one of these set of nodes, G, H, I, J, K, L. If I reach one of those nodes, I am guaranteed that I will reach my target node as well. Connect to each in a cycle, or does it just mean that all nodes that are connected in a cycle of any size? Brian Akins, so we can have both. We can have nodes that are connected to each other. So we can have just one cycle of nodes, or maybe 3 nodes all connected in a cycle, or we can have multiple connected nodes as this, but we have to guarantee that from every node here, I can reach every other node. See, from G, I cannot reach F, right? There is no way for me from G to reach F, because I can go to H, but I cannot go up. Neither can I go up from G to E as well. So G and F are not connected. But from G, I can reach any other node, H, I, J, K, L, from this, but if I start from any of those nodes, H, I, J, K. So that is a strongly connected component. Okay. Does the concept, so everyone else, does the concept of strongly connected components make sense? Of what they are and what they mean? So if it makes sense, and I know that it is already in the slides, how would you go on about solving? So given a graph, let's say that I would like you to find all the strongly connected components of this particular graph. How would you go on doing that? So let's see. What we need to do essentially is, and I want you guys to think about it while I talk. So what we need to do essentially is we need to shrink all our strongly connected components into a single node. And that would be sort of like a meta node that contains other nodes inside. And then we can connect all of those meta nodes together into a particular graph. Now, first things first, does everyone agree that strongly connected components, SCCs, are directed cyclic graphs? All strongly connected components are directed cyclic graphs. Do you agree?